right, let's now go into the second section, which is porting models with GroqFlow. And the agenda for today is how do we work with GroqFlow? What are the best practices for GroqFlow? And then we'll be looking into some examples of GroqFlow and how to debug GroqFlow if things don't go as expected. So let's get into it. GroqFlow is a very simple wrapper around our compiler and also our runtime. And all you have to do literally is within 3 steps, grab your model, grab your inputs, and use this API that we have. Is completely open source. It's called GroqFlow. And pass in your model and also your inputs into GroqFlow. So let's just do that step by step. Step 1, let's grab your model. And over here, we're using the transformers library from Hugging Face. We're grabbing GPT-2 along with its config. Go back. Step number 2, here's something with some asterisks attached to it. You need to specify your inputs in a dictionary format. So some of you who've used maybe Onyx Runtime before, you'll be familiar with this kind of setup. But for those of you who aren't, this is something you have to be mindful of. When you pass in inputs into GroqFlow, we'd like them to be in the form of a dictionary. All right. And for this, we have the input IDs and also the attention mask for this transformer-based GPT-2 model. There's also a few subtleties involved in this. Number 1, like Andrew mentioned, we work with static graphs right now. So over here we have, I think, the max sequence length, which we specify in advance. Sure, you can use smaller sequence lengths to run GPT-2. But the way we kind of work with static graphs is you figure out your max, and then you just use the same IOP, the same executable to run whatever you may have. We just pad it to get it to work. Otherwise, it wouldn't be deterministic. All right, and then what you do after that is you just pass it into the API call, the Groqit API call. You pass your model and your inputs into it. And like we were talking about above, this effectively abstracts all of the steps you have to go through within our software stack. So this converts to Onyx. It also optimizes your Onyx file. In the hands-on session, we'll be looking at Onyx graphs and also the difference between an unoptimized and also an optimized Onyx graph. And on the third step, we will check for ops support, and that's on the Groq layer, whether we can support those Onyx operations. We convert to float 16. Our MXMs operate on float 16, also operates on float 8, int 8, and I think even int 4 right now. But that's something to keep in mind. Once you pass something into our matmul engine, the MXMs, it's going to be quantized to FP16. And once you have your Onyx already, it compiles, assembles, and you have an executable, which we call the IOP. It's going to be saved in your users.cache file, and you can always look at the stats, and we'll look at that later on as well. But now that you have the executable, all you have to do is just use it with the runtime. All you do is you unpack this dictionary, and you get something which runs on our runtime on the Groq system. There we go. Now, what happens if things don't go to plan? It tells you where it failed. So for example, over here, it says checking for op support, which means we have an operation which isn't supported on the Groq system. And this isn't really something you can do right now because you'd have to tinker with the compiler. So like we were talking about earlier, contact us and we'll work with you to get things unblocked. However, if we had issues on other levels, this is something you can work with and most likely you can unblock yourself. All of the files I mentioned before, it's going to be in your cache folder. So if, for example, you had an issue with your Onyx graph, it's right there in your cache folder. You can play around with it, you can debug and try and move further. All right. So there are a few key functionalities within the GroqFlow and the Groqit suite. We have this Groqit API call, which allows you to compile models into Groq programs. That creates your IOP, your executable, and then this allows you to run that on your runtime. We also have a benchmarking API call, .benchmark, which gives you the latency and also the throughput for your application. Like we mentioned before, everything is deterministic, and for each given cycle count, you know where all your data elements are. This just tells you the total cycle count for whatever application you may have. All right. All this is just a quick user guide. I'm going to go through a few of these slides and then we can go straight into the hands-on session. So like I mentioned before, all you have to do is specify your model and your inputs. You can use PyTorch, Keras, Onyx, whatever kind of high-level framework you may have, that should work. And for some examples, for example, if you're working with a convolutional network for images, you'd want to be able to pad to your maximum length, your maximum dimensions. And for an NLP problem, you want to pad everything to the maximum sequence length. That's just some advice we have for you guys. You can specify the number of chips you'll be running on. So on the rack system you have at the ALCF, you have 8 nodes plus a backup node, and you'll be able to run anything up to a 8-node topology. So you can have a lot of fun with that. You can decide whether to rebuild with GroqFlow. So the default is whenever you run GroqFlow, we will rebuild the executable. But sometimes these compiles, of course, they may take some time depending on the topology. And in that case, you are more than welcome to just say, don't rebuild this. And you can grab the executable from your cache folder. You can specify different build names, so you save it in different cache directories. And this is just something which allows you to run with the runtime. Benchmark, Netron, which allows you to view your Onyx graph, and GroqFlow, which allows you to use our profiling tool to understand how your application is being ported to the hardware itself. I understand this is a really, really high-level overview, but we're going to go through some code, which is going to help things sit a little bit more. All right. I guess before we go into that, does anyone have any questions? I assume not. All right.
I don't see any questions in Q&A, but if they pop up, I will let you know.
Okay, sure thing. All right, so first of all, let's go to GroqFlow and go into the install guide. I'm working with a replica system. So this is a replica of the rack you have at ALCF. This should be the state you guys have it in, if I'm not mistaken. And we're going to go through a fresh install of GroqFlow, and we're also going to run a few applications. Let me just run this one very quick command. You can also run this yourself. And this shows you the topologies that you have within your system. So it goes all the way up to 72, which means you have 9 nodes with 8 chips. All right, so number one, we need to install GroqFlow because we want to be able to run our applications. Let me go to this public GroqFlow repository. So all you have to go is go to the public Groq repo, click on GroqFlow, and you have all the instructions you may want to install. So I want to go onto the install guide, and I want to install GroqFlow. Let's begin over here. The steps are all available here under trying out GroqFlow. And let's just go through them step by step. We've tested everything with Miniconda, by the way. You're more than welcome to use whatever virtual environment packaging system you may want, but we've only tested on Miniconda. So let's go through this step by step. Honestly, this is going to be the hardest thing you do today, and that's because they've changed Miniconda recently, and you can't just keep on pressing enter to get to the end of the license agreement. You have to time it perfectly. And if you miss, you have to run it all over again. So I'm gonna be very focused right now. Okay, so now we have Miniconda installed. Well, let's give it some time. It has to initialize as well. And you need to kill your current terminal and open up a new one. And once you do that, you're going to be able to see that Conda's installed. To verify that Conda's installed, when you start a new terminal, you can see this kind of virtual environment base set up over there. And you can even use commands like conda environment list. And right now we just have our base environment. And what we want to do is we want to install an environment for GroqFlow. So let's go back into our documentation and look at the install instructions. So over here, we want to create an environment called GroqFlow, which specifies the Python version. And this is a variable right now. So to be able to understand what kind of Python version you need to use, there's this matrix we have over here, which is dependent on your OS, the version of the GroqOS suite you have, and also, well, that's kind of what you want to figure out. So let's do that with our system. What kind of OS do we have? We have Ubuntu 22.04. And now let's find out the version of the Groq SDK we have. And for that, we have a command called tsb kernel version. The teacher is going to go in a bit more depth about this tooling tomorrow. So don't worry about this. We're just going through what we need for today. So we have version 0.10 and we have OS Ubuntu 22.04. And if we go back into the matrix, that tells us that we need Python version 3.10. So let's do that. And once you've made your environment, all you have to do is activate it and we're in. Okay, so now let's go back into the documentation. And step 2 says we should pip install GroqFlow. So there's two ways of doing this. Like you can see right now, we have the repo on GitHub, so you can just clone this. Or you can also use pip install and pip install it directly. This is available on the PyPy index system. What we're going to do right now is we're going to clone it because I want to be able to access some of the files within GroqFlow. So let's clone. Now that's done. Upgrade pip. It's always a good thing to do. I'm pretty sure it should be updated. Amazing. Go into GroqFlow and install GroqFlow. All right. And always make sure to use your current environment's Python. Yeah, this may take some time. And if that is the case, that's completely fine because I already have another system which he set up earlier. It's like a cooking show. Um, do, do, do. Okay, it looks like we're almost done. And there we go. We should have GroqFlow installed right now, and let me just double check that from GroqFlow import Rocket. Oh. Yay, we have it. All right. Now that we've installed GroqFlow, let's go through a few examples. I have a few examples over here in one of the other nodes within the rack system. Let me just move this Zoom system. Docked it up. Okay. All right. So let's start with just porting a few models. I have a really basic example over here. And it is simply just a generalized matrix multiply. It's a linear unit, so it's a matrix multiplied followed by a bias add. And what we do at the beginning is we import our high-level framework, so Torch and Torch NN as NN. We also import GroqFlow and Groqit because we want to be able to compile this onto the Groq system. What we do is we define our model. So over here we have NN linear, and here we have the dimensions. Let me just make this a little bit smaller, so that it compiles a little bit faster. Convert this into a dictionary such that Groqit will be able to function. I'm going to just comment out all of these lines of code, and we're going to focus on grokking a function. So let's do that right now. Python, let me save this first. GroqFlow.py. And as you can see, it's kind of gone through all of those steps. It exports to Onyx, optimizes it, checks for op support, converts to float 16, compiles, and also assembles. What we haven't done yet is we haven't run it. And I don't want to recompile this. So I'm going to set this rebuild file flag to never. Let's run that again. We run it. What we haven't done yet is print the output. So let me just do that really quickly. All right, there you go. You have a linear model with the first layer of an MLP running on the Groq system. So what we could also do is compare this to what you'd get on the CPU. So for that, let me just change the dimensions to 1 because it's easier to compare one value. Print the Groq output and also print the CPU output, which is output. What's going on here? So we got the wrong input dimension shapes. No, that's because I used the system in the cache and I didn't rebuild it, even though I changed the dimensions. That's fine. Let's just rebuild and it should be okay. And there you go. You have on the top row, that's going to be the Groq output, and on the bottom row, that's going to be the CPU output. And
but shouldn't the compiler should have caught that change, and that should have invalidated the cache. Is that a bug or?
No, that's just because I set this rebuild flag to never.
Okay.
Yeah.
And are there any other values you can put there or not?
It's either always or never. So always just means if I were to change this file even, it will just rebuild everything. And never just never rebuilds. Does that answer your question, Bill?
Yeah.
All right.
I just wanted some clarity there.
So over here on the top row, we have the Groq output, and at the bottom, we have the CPU output. And the difference between the two is because on the CPU, we're using float 32. And on the Groq system, as you can see in this line over here, we're converting to float 16. That really explains the difference between the two. And if you wanted to, you can also change these steps and not compile on the float 16 Onyx, but compile on the float 32 Onyx. And you're going to have a value very similar to the CPU output. You can change the data types as you please, depending on your Onyx graph. All right, so maybe now's a good time to look into your cache folder. So it says everything is saved in your users.cache, hidden.cache file. And we have that over here, .cache, GroqFlow, and everything is named based on the file name you have. So my file name is GFlow, and all the files are going to be in GFlow. We have the Onyxes, so we have the original Onyx graph, the optimized Onyx graph, and also the optimized float 16 Onyx graph. And we're using offset 16 for Onyx over here. So that's what op16 means right there. And maybe we can have a look at how these Onyx graphs look. So let me copy an Onyx graph and paste it and see how that looks. I'm using Netron, by the way, and that's an open source repository, which allows you to visualize these Onyx graphs. And as you can see, this is the static input graph, which we feed into the compiler. You have your input, you have your matmul with the fixed dimensions, and also the data types, and your output. Note that it says float 32 over here, and the output's float 32 as well. If we go back and let's say we use the float 16 Onyx instead, you can see we're using float 16. So I'm sure that's obvious to all of you, but I guess the point is everything is available in our cache folder. And you can also see the output of our compiler. So here are the compile logs. This accepts an Onyx graph, and then it schedules all the instructions, goes down. And because everything's deterministic, even before you run it on the chip, it tells you the cycle count, the compute latency. And all this is just a division of the cycle count by the clock speed. So that's 366 divided by 900 megahertz. That's all the compute latency is. And we also have some other stats adding IO in the form of theoretical PCIe. We also have logs for the assembler. And all this just says is, I can't read the top because Zoom is blocking me, but I assume it just says it worked really well. So everything is in your cache folder. If anything were to fail, you can look at the logs and it'll tell you where it's failed. So let's end this example really quickly and go back to GroqFlow. Okay, and look at the other functionality which we have within GroqFlow.
Sanjeev, is there a way to change the location or the cached file? Or is it all in the default one?
So that's the default. I think there's a flag. I'm not sure if it's on the documentation or it's public right now, but that's a good question. I've definitely done it before and I specify a different cache file, but I can't remember how to do it off the top of my head.
I can look into the documentation and try to share that in the chat.
Yeah, sure, thanks.
Even in this over here. No, that just saves it. Still in the same file, but under a different name. So yeah, thanks, teacher. Okay, so now we can use the benchmark. Let's look at the benchmark tooling. All right, so you can specify grokmodel.benchmark. You can call that that method, and then within the method of within the output of the method, all you just do is specify the attribute .latency, and it gives you the estimated latency. So this uses the theoretical value of cycle count divided by the clock speed, and it also adds theoretical PCIe overhead. We're working on adding actual runtime numbers to this value as well. But right now, these numbers are theoretical. Although everything which happens on the chip, that's deterministic, and we know how many cycle counts that's going to take. All right. What you can do as well is you can use Netron from your Groq model directly. Let's just quickly run that. So this is literally just going to show you the same Onyx graph that we had before, but it's using the GroqFlow API call. There we go. And probably the most interesting for you guys right now, that's going to be using the GroqView flag. And to use GroqView, you have to specify GroqView within the Groqit API call. And to make this more interesting, let me change the dimensions of our model. Let me go to 320 by 320. And the reason I'm using 320 instead of a power of 2 is because our vector length is 320. But of course, we can use literally any number. All right. So Hatice is going to be talking about this a little bit more tomorrow when she talks about the GroqWare suite. But for now, let's look at how you can use GroqView to profile an application which you may have run, you may have compiled on the Groq chip. So over here, we have a linear layer. So we expect the units to be the MXMs. So you can see the MXM utilization to be fairly high. And also the VXMs. Where are the VXMs? Yeah, there you have over here. So as you can see over here, we're utilizing the memory slices of the Western Hemisphere and the MXMs of the Western Hemisphere. If you remember from earlier, the chip is symmetric along a vertical axis, and you have matrix multiplied planes on either hemisphere and also memory slices in either hemisphere. So what's going on here is we're extracting data from the Western Hemisphere, bringing it to the Western matrix multiply unit, and then saving it in the Western Hemisphere as well. You can see a little bit more about what's going on within this application. And we can also, as you've seen before, look at the streams as we flow through the application. On the top over here, you can see the streams going eastward, and on the bottom, you see the streams moving westward. So right now you can see the elements being accessed from memory, going through the MXM, which is the matrix multiply unit, and then coming out and being saved in memory again. And like Andrew was mentioning before, if you were to pause it at any given cycle count, this is going to be the state of the chip at that precise cycle. Okay. There's also another view called the schedule view, and that shows you how the data moves across the chip. It's very similar to the stream view, but it just changes that time dimension into a physical dimension. So as you go down the y-axis, you're increasing in cycle count, and you're seeing how data moves across the chip. So over here, data is being read from memory and then being passed on to the MXM to perform that matrix multiply. All right. So that's GroqView. And I believe with that, we've concluded the section of GroqFlow in which things work according to plan. And if that works for your application, we're so happy for you. But sometimes things don't work according to plan. And I have a few of those examples up top. GPT-2. All right. So maybe we can look at a GPT-2 example. And one of the ways in which GroqFlow can fail is if it allocates not enough chips for application. So each of our Groq chips, each of the LPU units, they have 230 megabytes of SRAM. And for quite a few applications, for example, these large language models, it's insufficient to run on a single Groq chip, and therefore you have to deterministically network outside of a single chip. And let's see what kind of happens if we don't specify the num chips flag. This will try its best, GroqFlow will try its best to allocate however many chips it thinks an application may need, but in some instances, you may have to specify this yourself. So let's go to Python, run GPT-2, and then see how that goes. This may take a bit of time because GPT-2 is a fairly large model. If I remember correctly, I think it's around 240 million parameters. But let's see how this does. And for those of you at SC, I think we actually presented this at SC, and we didn't quite have enough time to go through this step by step in code. So we're doing this right now. As you can see, it's compiling the model, and sometimes for some models, especially large models, it may take a bit of time. But what we have noticed is going from SDK version, the time to compile actually decreases. So this is something we're actively improving on.
Can you quantify it a little bit or not? And like, for instance, Llama 7B, how long does that take to compile?
I think Peter tomorrow will be able to talk about that a bit more, but
Okay.
the compiles that I've done for Llama 7, not Llama 7B, but I've done GPT-2 compiles with the Llama 7B methodology, and it takes a few hours, about 4 hours. But the beauty about these large language models and these foundational models is you kind of compile them once and then you run them thousands and thousands and millions of times. So that kind of one-off is completely fine.
And I guess the other question is, how does it scale with size?
How
The
does
compile time?
How do the compilation times, or how does
the compile time scale with model size?
Generally, the compile times increase as model size increases. It's a general rule. However, I have seen a rack scale compilation compile faster than a single chip compilation. So it's also kind of application dependent.
Thank you.
And I guess while we're talking about large language models, GPT-2 is technically a large language model. And as Bill was talking about, we have Llama 7 billion running on this rack system. That model isn't using this GroqFlow tooling. We're using a few optimizations under the hood to be able to extract all that performance. And Peter will be talking about that tomorrow in that dedicated 1 hour long LLM session. So even with GPT-2, we can do all those optimizations, for example, caching all of the keys and all the values within persistent memory on chip. And if I remember correctly, what you do is you increase performance even for this model, going from GroqFlow at 30 tokens a second to using this slightly more complex methodology with KV caching, going to 30,000 tokens a second.
Also, I don't know if anyone is following along in the audience, but if you have any questions for any of the steps that Sanjeev has talked about so far, please feel free to ask. We also have the Q&A tool that you can utilize if you don't want to ask live. So let us know.
Yeah, I'm not sure if we should stay here. I can't remember how long this took, but I guess we can go on to our next application. So maybe we can go into GAT. So here are one of the applications which we actually do really, really well on, but out of the box, it doesn't quite work with GroqFlow. So this is an application from Torch Geometric, and this is a library for graph neural networks. The reason why this library is a bit tricky is because even though it's a superset of PyTorch, it includes these third-party libraries which don't necessarily have operations which export to Onyx really well. And you can see how that would work in this situation. So all we do is we specify a model from this PyTorch geometric library. In this case, I'm using graph attention transformer, and it's just transformers, it's attention on graphs. I specify that model, get a few inputs, and as before, pack them into a dictionary and use Groqit to run. Let me start up a new terminal, activate the GroqFlow. Actually, let me activate MLA. Okay. And then run this application. All right, so we get a bit of an error message down here. And it tells you exactly what's going on. Torch.onyx.errors. The scatter reduce A10 op on Onyx version 16 is not supported. And this is something which, even though we care about completely, it's something which is independent to Groq. It's something within the PyTorch and Onyx layer itself. There are different ways of going about it. I would recommend if you were to face this issue, go online and just Google this very exact issue. And there are multiple workarounds for unblocking yourself. Number one, you can use Onyx script. And what you can do is you can write your own operations within Onyx as a composition of other Onyx operations. And something else you can do as well is you can register Onyx operations within PyTorch. So for some, for some use cases, if let's say I were to go to Onyx. This is a list of all the operators within the Onyx ecosystem. In some cases, you have operators which are within the Onyx ecosystem, but there just isn't an export from PyTorch to Onyx. And in that case, all you have to do is literally just register these operations within PyTorch. And you can unblock yourself almost immediately. So this is one issue which you'll probably face if you try and work with graph neural networks, and also kind of any model in which there's a problem with the PyTorch or the TensorFlow to Onyx ecosystem. So just letting you know, if you do get this issue, it's something you could probably unblock yourself. Still, please do let us know, because we'll always contribute to these third-party libraries and try and unblock them for you. But if you do face this, it's something you can definitely do yourself. It may take a bit of time, but you can definitely do this yourself. Okay, so let's see if That's still assembling. Let me go to another example, which is non-max suppression. And this is, for those of you who haven't worked with non-max suppression, it's usually at the head of a YOLO model, for example, these computer vision models. And the reason you have non-max suppression is sometimes you have a lot of candidate boxes for your target bounding box, and you want to do intersection over union over them. This may be dynamic. For example, you may have an unknown number of boxes at the end of your prediction, and that's something which we do struggle with, dynamicism. It's something we can work with, but for now, we don't quite have the support. So let's try running this example. Python non-max suppression and see how we do. Okay, so here's another error you might face. And it's an error within the Groq system itself. So it says, your model has these ONNX operations which aren't supported by the compiler, non-max suppression. Please replace these operations. That's something you can do, or let us know. So one of the ways you can unblock yourself if this were to happen is, let's look at the cache folder for this specific application and its non-max suppression. So look at the ONNX graph. It's going to be a very simple ONNX graph. Let's still see that. Path, Metron. So that's the application we have over here. You can see the offending operation, which isn't supported by the Groq ecosystem right now, is non-max suppression. What you could do is you could write your own node, register that within ONNX, or you could use something, for example, ONNX graph surgeon, and literally just cut this out and go from step to the other, and maybe have another node which just keeps the same dimensionality which you'd want. That's something you can do as well. Depending on how far you get with this, you'll be able to find a model which is identical to what you want originally. Or maybe you just have kind of a no-op, which allows you to compile. It won't give you the exact results, but it also gives you an understanding of what performance you may get. So this is something we do internally at Groq, where sometimes if something weren't supported, we just try and ignore this operation and just still try and gauge how well we perform. That's something you may be interested in doing. The option's on the table, but I would definitely recommend just coming to us and saying, this is something we could be interested in. Can you work with us on getting that supported? All right, so that was actually my final example. And let's go back to the original example. And apparently it seems as though this has worked. And it didn't work yesterday, so I'm very, very curious as to what's going on. So let me try running it. Not going to rebuild this again because that will take a bit of time. Let's see how this goes. Okay, loading it. Oh, of course. I just used the wrong inputs. All right, so this is actually a different error. I haven't seen this one right now, so you're going to be seeing me debug this live. What's going on? That's a default. Okay, so this looks to be a runtime issue. Let's look at the logs and see if we can get anything from there. I doubt we would because this is at the final layer once you've already compiled and assembled everything. Let's see. Okay. Let's look at the log compile. Yep, everything's fine there. You get an understanding of the cycle count and an understanding of the performance. And like I mentioned before, with these large language models, some of them you can use GroqFlow on, but to extract the most performance, we have our own custom flow, which we'll be discussing tomorrow. And for this, you go from 30 tokens a second to 30,000. So it's something you want to look into if you want to run these large language models. But let's go into what's going on here. Honestly, this is something with the runtime, and I'm not particularly sure how to debug this. I would probably ask Aviv tomorrow, but you do have your compiled IOPs and everything out here. So I do wonder what's going on, but we'll debug this later. What I was wanting to show you was yesterday, this couldn't compile on a single chip. And once you go to log compile, it just says, the model doesn't fit on chip memory, please try more chips. And then kind of the way you unlock yourself is you just go from this kind of setup to going to a setup where you say num chips equals to 8, or maybe 16, or 32, or so on and so forth. GroqFlow tries to specify the number of chips automatically during your compiles, and what this does under the hood is literally just dividing the parameters multiplied by the data type, so how many bytes you have in your model, divided by how many bytes of memory we have within a single chip. So it's a very crude understanding of it, but it works most of the time. All right, that concludes the GroqFlow section.